Streaming is on. Recording is on. Oh, no, no, not that. And then we're good to go. Okay. By the way, did you notice that there is a typing mistake in my slides here? All becomes obvious, I think, when you look at that. You know, it's in this last line. This line. You see it? Minus. Plus. This is supposed to be plus. What? No? No, it's all. So what is it then? Oh, hold on. What about this? That's supposed to be 1. So that's a typing mistake. So I would like to apologize that. But is it making you more difficult to understand the concept, or you're still good? Not changing anything here. Okay. Again, you understand that what we did is that we want to, I think that this is what really nicely summarizes, what we did. So I wanted to use the concept of virtual work in order to find the static equilibrium. And the way that I can use it is that I wanted to set this equation to be equal to 0. And the only way that I can set this equal to be 0 is that the displacement, meaning virtual displacement, have to be kinematically possible, kinematically admissible, something that is not violating against the constraints. How can I make it happen? Well, the story goes such that first I'm finding the relation between global coordinates and generalized coordinates. All right, so that's my first relation. But more important than that, I have to find a relation between independent generalized coordinates and all the generalized coordinates. And that relation is this one, that was based on coordinate partitioning. Coordinate partitioning, where I categorize my coordinates to be dependent and independent. So once I use this concept, then, and only then, I can set this equation to be equal to 0. And once it is set to be equal to 0, then I can find where the static equilibrium is located at. Clear? Makes sense? Because if I'm just introducing virtual displacement to all the generalized coordinates, then I'm violating against the constraints, and there is no way to find the static equilibrium. So that's the kind of story in a nutshell. And this is exactly what we're going to redo again when we are applying this to dynamics. No difference whatsoever. Again, we're going to go to this equation that is setting not the static equilibrium but dynamic equilibrium. And this time I'm expressing the virtual displacement again with this concept, making it possible to set this equal to 0. That's it. That's almost the whole story. There is one tiny problem still. And tiny problem is related to this guy here, which is generalized coordinates or acceleration of generalized coordinates. And that's an annoying problem because, look what I have there. That's all the generalized coordinates. I don't want to have that. I wanted to express also the acceleration by using independent generalized coordinates. So that forces me to use this coordinate partitioning technique again, but this time for acceleration level. And this is when it becomes mathematically involving, mathematically nasty. Don't get confused about the details. Keep the big picture all the time in your head. Think about that. You just wanted to express, okay, let me make this clear. You wanted to express this guy such the way that is not all the accelerations but only independent ones. That's the final challenge. And also, good you to know that generally you cannot do the selection as you want, because there is this possibility that when you're inverting your, let me see where it is, I need to go all the way. Where is this story? Here. This is telling you how is a relation between dependent and independent generalized coordinates, and this was based on coordinate partitioning. And I said earlier that you can do this selection as you want, but actually you cannot do it as you want. And why is that? Because look at that. You have to be able to invert the dependent part of the Jacobian matrix. Sometimes you're unable to do it. Sometimes you just cannot do it. If you have a poor selection of independent coordinates, then that reflects the fact that this dependent part of the Jacobian matrix is not invertible. And that's something that you have to make another selection. Of course, if you think about the computer implementation, you cannot just keep on trying that, but there have to be an automated way to do it. And there is an automated way to do it because you can use a Gaussian elimination with the column pivoting. Column pivoting, this is something that you don't need to know in details, but if you wanted to Google it and you wanted to learn the details, then it's a Gaussian elimination with the column pivoting. What is that? It is actually taking your Jacobian matrix and is starting to reorganizing the columns of your Jacobian matrix such the way that what becomes in the left-hand side of the Jacobian matrix will be invertible. What is left is not, is independent ones, and it's giving you the ID numbers, how this column pivoting was changing the ID numbers. Because remember, each one of the columns in a Jacobian matrix are associated to generalized coordinates. And now we're starting to changing the order of the generalized coordinates, but that's an automated procedure, so it's called Gaussian elimination with column pivoting. That's what it is. And you can, if you wanted to study that in details, I'm sure there's lectures available in Khan's Academy. So Gaussian elimination, I think the Gaussian elimination, was it mentioned somewhere here? Here, Gaussian elimination with column pivoting, meaning that is allowing to change the order of columns. There's a way to make it happen. Then it's doing that for you automatically. And actually in a computer implementation, coordinate partitioning is used with Gaussian elimination with column pivoting. And that's a little bit of a problem because to be in a safe side, you have to do this selection about the dependent and independent every single time step. Because it's possible that if you don't keep on updating this selection, then you end up to have the problem where this dependent part is no longer invertible. And then that's when the simulation will break. So in a computer implementation, they do that every single time step. Or if not every single time step, then frequently anyways. Okay. All right, so I was about to explain this last thing that we need to do. So we need to go ahead and use the coordinate partitioning in acceleration level. And once we are done with that, then we get to solve equation of motion a little bit in a different way. Now, what we're going to do is that we're going to take this Jacobian matrix multiplied by acceleration, and this is where we actually express, or this is where we're going to use this coordinate partitioning technique. So it's going to be mathematically very involving. So we're going to go ahead and use it in this particular equation. So we have here dependent acceleration, and is expressed by independent ones. And this is something that we are already familiar with. And then there is one more component that is left, and it's coming from this part here, and it's going to can be written like it is shown here. And here is the monster guy that we are already familiar with. That's the one we're using also in the method based on Lagrange multipliers. Okay, again, it looks bad, and it is bad. But again, we just wanted to use this coordinate partitioning in acceleration level, and we're going to make it happen in this equation. Okay? Now, once we have all the acceleration, we can use these dependent and independent parts. Using the definition we got from the previous slide, we can find this relation and we are able to express this independent acceleration as it is shown in this equation. Now, this is the core content, so it's quite mathematically involving, so it needs certain components, but everything is or will be doable. The final step that I'm doing here is that I'm just calling these matrices with the different names. I'm going to call this as a B for the reason that is unclear. I don't know why it is called B, but I'm just going to call it B to make it clear and simple. And then this I'm going to call as a D. And then once I'm using these notations, my equation of motion can be expressed as it is shown here. And now this is a minimum set of differential equations. So if you have a pendulum structure, planar case, following this procedure, how many unknowns you will have in this case? 1. Not 5, but 1. There are always these magic numbers that are number of generalized coordinates and number of constraint equations. What you do with those numbers in case of method based on Lagrange multipliers, you will adding them together. In case of embedded technique, when you substitute a constraint inside, you have here minus. You got it? You're absolutely sure about that. Okay. Now I have this example. This is a system that we have studied in, also with help of Lagrange multipliers. Now I'm going to redo the whole thing. I'm going to express the equation of motion by using this substitution technique called embedded technique. So one moving body, meaning 3 generalized coordinates. 2 primitive joints. How many constraints? 2. Then my question to you is number of unknowns. What will be the number of unknowns in this case? Now let me put the Socrates on, just a second. What was that? Oh yes, it's going to be this method based on substitution. Hold on, my Socrates is not yet set, so let me put it on. Oh, no, here. Socrates, I hope that it is a teacher locking here. All right, so I'm almost there. Okay, so Socrates is on. So let me go back here. So in this example, we are using the substitution technique. So we're using embedded method, where we're embedding the constraints inside of the original equation. What is a number of unknowns? Choices are 1, 3, 5, 6. Only one is correct. Well, which one is correct? Is it difficult? Not difficult at all. Basically 2 choices that you have to select the correct number out of the 2 choices, but which is a correct choice? Okay, so let me take a look at this. Okay, so I have 59 students. Okay, so what do you think? Is it going to be even a thin chance that this is going to be 100% success rate? Not today. Maybe. I don't think so, because there is always the guys that are watching the phone, following the laptop, doing all kind of stuff, but not listen to me. And then when the in-class quiz comes in, then it's too late. It's simply too late. Okay, but you guys all done? '70 students, roughly 71 students, 51 already entered the answer. 60. So 11 are still thinking. You all done. I don't expect to have 100 participants today because timing is not good. Timing is middle of the day, and the online participants. I mean, these students that are studying remotely. I don't think that they have an opportunity to follow the lectures during the day. Okay, so I have 8 students that are still thinking. So can I go? So okay, so in 5, in 4, in 3, 2. Okay, 1. Okay, so can I close now? Okay, guesses. How much is the success rate? 93. 93. Really? Okay, now I can see that, the last minute people are logging in. They have no idea what's the correct answer. So we should try to cut this soon now. So what is it? 79. Yeah, I think so too. 70 something. So the first number is 7. I don't know what's the next one. Okay, we done? That's what I say, 74. 74. Okay, so there are 2 choices that make sense, a little bit of sense. And these 2 choices are 1 and 5. 3 makes no sense because, we have never discussed about this opportunity that we have 3 as an unknown. That's just never been in a table. 6, no good at all, because where the 6 would be, where that is standing for, there is nothing that is corresponding 6. So the correct answer here is 1, because we have 3 generalized coordinates, 2 constraint equations, 1 differential equation. So it's 1 differential equation you need to solve the response of this system. Now, you may wonder, if this is a superior method, if this is always much more efficient than the one based on Lagrange multipliers. And answering that question is more complicated than you may have thought, because the method that is based on this substitution technique requires Gaussian elimination with the full pivoting. And that sometimes takes quite a bit of CPU power to do it, because if you have a large system, it's not that simple to carry out. So it's not easy to say what is more efficient than others, and it actually depends on your application. Then also good you to know that these 2 methods that we've been studying in this course, they are within the family of global methods. And then there are methods that are based on system topology. And those typically are very efficient methods if their system is large. And if you're looking for real-time applications, and then particularly if you have a very large system, the method based on topology are the most efficient ones. And we haven't touched them in this course, and we will not touch them in this course. But, generally speaking, it is a little hard to tell which is the most efficient method, because there is no such thing that is always the most efficient method, but it depends on your application. There is still something good to know. Multi-body system community, roughly speaking, at least in a history, there were 2 strong communities. One was American community, another one was a European community. And the American community was a big favor of the method based on Lagrange multipliers, whereas the European community was very much fan of the method based on coordinate partition. Still, both are very good. Which one we prefer? American way. Why is that? We don't, because my supervisor was Ahmed Sabana from Chicago, and he was about big fan of Lagrange multipliers, so that's why I'm too, and you too. So it goes in the family. So even though we're located in Europe, that doesn't matter. So the supervisors are, they're telling you this is the good method. Use it. Use that one. So I'm saying you use the Lagrange multipliers. Actually, makes no difference. Okay, let's look at an example. So how is that we can solve this example using the embedded technique? Now how it goes, we're gonna take first certain steps. Again, same procedure like in the case of Lagrange multipliers, meaning no thinking. Absolutely no thinking. You're just following the certain steps, and then you automatically end up to have an equation of motion. Okay. First step, mass matrix. And of course, I could use, this very sophisticated mathematics to define all these components, or alternatively, I could use pre-calculated tables. Either way, I need to get 3 components. First one is the one that is associated to translational coordinates, and it will be 2 by 2 identity matrix, where the mass of the body will be located in diagonal components. Then the second one will be mass moment of inertia, and it can be computed by using these volume integrals like shown here. I don't think that you necessarily need to do it this hard. Let me see. Yeah, I don't think that you need to do it this hard way. And there is make an assumption that thickness is insignificant. So the y direction is simply ignored. So I think that you can make it happen if you have a slender body. So then what it is enough is to do this integration, integrating over the x direction. So basically you do it like it is shown here. And once you do all the math, then so it's a little bit unclear story. But once you do the math, then you will get this mass moment of inertia, that is mass multiplied by length power 2 divided by 12. We will have diagonal representation of mass matrix because body reference coordinate system is located in the center of the mass. So there is no need to compute that off-diagonal components because it will be automatically equal to 0. So that's the first step, mass matrix. Then externally applied forces, so exactly the same procedure than the last case, no differences whatsoever. So we're gonna just simply look where the forces are applying in the system. And now there's one force only that is applying here in the center of the mass, and that's where the body reference coordinate system is located as well. Okay? So the force in a global coordinate system can be expressed like shown here. This is a kinematics where the force is applying. And once you differentiate that kinematic expression with respect to your tenorized coordinates, you end up to have a mapping matrix that is reading like shown here. Okay? That will be multiplied by forces, and then you end up to have a forces in tenorized coordinates. So you have 3 components, one that is associated to Rx, second that is associated to Ry, and third that will be associated to angle theta. Okay, so end of the step number 2, step number 3. So we're gonna construct the quadratic velocity vector, except we don't need to do that because again, here body reference coordinate system is located in the center of the mass. That will lead to diagonal representation of mass matrix, which in turn will lead to 0 quadratic velocity vector. Okay, then constraint vector QC. That's something that constructing the constraint vector QC. Okay, that's the one that I need in order to find this relation. This I'm not sure if this denotion, this should be correct denotion or not. Anyways, what I'm going to do now is that I'm going to apply the coordinate partitioning to my Jacobian matrix. Now I'm not going to use this Gaussian elimination with a full p-voting, but instead I'm thinking that there will be no numerical difficulties with my selection. And my selection this time will be such that the first 2 tenorized coordinates are my dependent ones. And the rest, which is the one component, scalar component, angle theta, will be my independent one. Okay? So this is my dependent part, this is my independent part. And again, those are associated to Rx and Ry, and this is angle theta. And now I'm ready to express the relation between all the generalized coordinates and independent generalized coordinates, and I'm computing this CDI, the one that is needed in order to construct this B matrix that is very essential to express the relation between all the generalized coordinates and independent generalized coordinates. So without further thinking, I'm simply using this 2 by 2 identity matrix, which by the way is very convenient because now this matrix inversion will be nothing. It's going to be still identity matrix. So what is left is this one here. My B matrix reads like it is shown here. So it's quite a fast, but hopefully you get an idea. And then the matrix D, that will be my next thing to do. So here, this by the way is the most cumbersome one. So here I need this dependent part again. And then, this part will be the painful one. This will be equal to 0, as will be this one as well, because we have no constraints that are a function of time. Okay, so the middle part, this is the one that it will be non-zero. So first I have my Jacobian matrix, and that will be multiplied by velocity. And I can see that there is a little bit of problem here because this is supposed to be once. Typing mistake. You see that? Because here. So one. Yeah, I think this is simply, because what I'm supposed to have here is Jacobian matrix multiplied by velocity. So this obviously is supposed to be once here. So there was a typing mistake. Can we set some kind of competition regarding the typing mistakes? So if you're able to find a typing mistake, it's always worth of, what would be a good prize for finding a typing mistake? What? What is that? Bait somersault. Oh, that's a lot. So that's a high stake. So that's so you say that if you're finding a typing mistake, you will have an office ready. Are you coming to my office then, or would you like me to stay in my office? So are you coming to my office? Say, okay, get out, take your stuff, get out. I will be here next. So need to think about it. Yeah, let me think about it. Anything a bit lower than that?
1.1 points.
Yeah, okay. Okay, so I need to set the rules. I need to think about that a little while, but I will come back to next lecture, and if there, something reasonable, something that is still worth a look at, makes sense to look at. So it's not just, I say thank you, and would you like to have a coffee? But something that makes sense, okay? So I was here. So now I have my Jacobian matrix that will be multiplied by velocity. This is what's going to be a result of that. And now I'm differentiating that with respect to my generalized coordinates. And now this is how it's going to be. So it's going to be a matrix, 2 rows, 3 columns. And that eventually will be multiplied by velocity of generalized coordinates. Let me see. Yeah, it seems to be all correct. So that's how it reads. And then I'm ready to move on. So I have this dependent part, this one here that is coming from the coordinate partitioning. And then this part here that is that we computed in the last slide. This is going to be what is left. And the D can be written like shown here. The final step will be assembly part. So I'm going to go ahead, take the B here, take the D here, take the mass matrix here, and then just put everything, and then the external applied force is here, and put all these components in the right place, and that's how the differential equation look like. Look, so it's going to be one single differential equation that gives you the angle theta. Rest will be solved by using constraints. So they are not even something that you solve here, but you're only solving the independent ones. If you wanted to find out the rest, those you can find it out by using a Jacobian matrix. This relation that we looked previously. How you like about this method? Kind of makes sense. Okay, so summary. Embedded technique versus augmented formulation. Again, embedded technique is the one that we substitute in the constraints inside of the original equation of motion. Augmented formulation, we adding the constraints with help of Lagrange multipliers. Okay, embedded technique, equation of motion are based on coordinate partitioning, meaning that you have to use this Gaussian elimination with the full pivoting, which sometimes needs quite a bit of CPU power, and you have to invert certain part of the Jacobian matrix. Then equation of motion do not include the reaction forces because they disappeared once we do the substitution. Then it gives you only very few number of differential equations. That number is actually equal to the number of degrees of freedom. Okay? Augmented formulation, large number of equations because the generalized coordinates and constraints will be added together. Not subtract, but added together. And then equation of motion are relatively simple. Well, yeah, they may be. Reaction forces are included to your results. So those are the two things. Then a few tips to mechanical modeling when you're doing your simulation assignment. Verify your model frequently. Keep on, watching how the model behaves. And if it behaves in an unexpected way, figure out why it's actually doing it. Is that the feature of the system you're starting at, or is it something that you have made a modeling mistake? That's something that is very important you to keep in track all the time. Verify the number of degrees of freedom. That's the thing that is good to keep in mind all the time. Make sure you understand the physical meanings of all the parameters in your model. This is a lot to say because typically there's a lot of parameters that you need to tune. Those may be related to integration procedure, may be related to friction and so on and so forth. But still, you're the one that is responsible what those parameters are. You have to understand what they're standing for. That's critical. By the way, this parameters comes particularly critical when we're looking at the hydraulics, because the hydraulic modeling is full of different kind of parameters that may or may not have a clear physical interpretation. Nature is very different comparing the simulation of multi-body system, because everything so far is kind of clear, exact science, whereas in hydraulics, they are not so exact. That's my personal opinion. Now, then, do not merge rigid bodies by fixed joint. Why is that? Because if you use a method based on Lagrange multipliers, you keep on adding the number of unknowns for the reason that is not needed. So don't do it. So it's considered as a very poor modeling practice. Okay, so analyze, visualize your model as frequently as possible before, try to find the static equilibrium. And then this is important. Think. And then think, and think one more time before you do things. This is not really a big problem in MATLAB environment, but particularly when you're using other commercial softwares, people tend to have very high frequency when they're clicking their mouse. So the frequency goes all the way up to 100 hertz, meaning that there is absolutely no thinking. It's just keep on clicking things. Don't keep on clicking things, but thinking things. You see what I'm saying? No clicking, but thinking. Can you recognize the difference? Good. Okay. Then, next will be hydraulics. And I said that today we're going to close early because I want to show my soft side to you. So let's close early today. Look, it's 5 to 4. So not just the 2 minutes, but the 5 minutes. 6 minutes actually. So what is that? Very, very flexible thing. Okay. Next week we're gonna start the new chapter in the course. So the new chapter is hydraulics. I'm gonna add one more lecture notes. So there's gonna be a second part of the lecture notes that will be available in a Moodle database. Take a look at that prior to lecture on When was it again? Thursday. Okay. So, see you on Thursday. Take it easy and have fun. Okay.